At first glance, it presents an imposing silhouette, a purpose-built, 8-wheeled armored vehicle, its form dictated not by aesthetics, but by the immense internal volume required for its power plant and cooling apparatus. This is no mere flatbed with a module bolted on. The integrated chassis and weapon station speak to a holistic design philosophy, a ground-up conceptualization of a mobile air defense laser. The vehicle's structure is a marvel of material science, a direct response to the dual requirements of mobility and survivability. The crew cabin and critical electronics enclosures are not fashioned from simple steel, but from advanced composite armor, a sophisticated laminate of high-hardness ceramic tiles bonded to a backing of woven aramid fibers, all suspended within a thermoset polymer matrix. This multi-layered approach is designed to defeat small arms fire and artillery fragments by shattering incoming projectiles at the ceramic face and catching the resulting spall with the high tensile strength aramid weave. The entire chassis is engineered for extreme rigidity, designed to absorb and dampen the severe shock and vibration of traversing rough terrain at speed, a non-negotiable requirement for a system whose combat effectiveness depends on maintaining the nanometer perfect alignment of its internal optics. The most prominent feature, the heart of its aggressive posture, is the unmanned turret. The engineering challenge here is immense. The system must maintain a pointing accuracy measured in microradians, as even the slightest vibration or structural flex would send the beam meters off target at its effective range. This reveals the core design compromise of the entire platform. A massively heavy and robust vehicle is required to carry the power and cooling systems, yet the weapon itself must be as lightweight and agile as possible. The LY-1 is the engineered solution to this paradox. At its core, the LY-1 is a 150 kiloballard class solid-state laser weapon. The choice of a fiber laser architecture is a deliberate one, driven by the harsh realities of fielding such a system on a mobile platform. While slab and disc lasers can achieve high power, fiber lasers offer a superior solution to the paramount challenge of thermal management. The heat generated within the laser is distributed over the immense surface area of many kilometers of hair-thin optical fiber, rather than being concentrated in a single large crystal, making the process begins with arrays of semiconductor laser diodes, which convert electrical energy into photons with brutal efficiency. These photons are pumped into thousands of individual silica glass optical fibers, each doped with the rare earth element ytterbium, which serves as the gain medium. Within each fiber, a cascade effect amplifies the light. The true innovation, however, lies in how the outputs of these thousands of low-power fibers are combined into a single, coherent, high-quality beam. This is achieved. These components are polished to a surface flatness measured in fractions of a wavelength of light, typically L20, and then coated with dozens of layers of dielectric materials using ion beam sputtering. These coatings are engineered to be hyper-reflective, achieving reflectivities greater than 99.99% for the specific operational wavelength, and possess a laser damage threshold capable of withstanding energy densities exceeding 40 G/2 for nanosecond scale pulses. Any imperfection would cause the optic to absorb energy, heat up, deform, and ultimately destroy itself in a catastrophic failure. To generate this torrent of photons, the LY-1 relies on a sophisticated hybrid power architecture. The primary source is an 800 kiloballard tactical quiet generator, a multi-fuel turbine engine capable of running on diesel or JP-8 aviation fuel, housed in an acoustically shielded and armored compartment. This generator provides the sustained power needed for long-duration operations and, critically, for recharging the system's energy storage. Supplementing the generator is a large bank of high-power density lithium-nickel cobalt aluminum oxide LY-NCA batteries. This hybrid arrangement is essential for tactical flexibility. It allows the LY-1 to operate in a silent watch mode, using only battery power to run its sensors and systems without the thermal and acoustic signature of the generator. More importantly, the battery bank acts as a massive capacitor, capable of delivering the instantaneous multi-megawatt surge of electrical power required to fire the laser. A turbine generator simply cannot spool up fast enough to meet this demand. The true magazine depth of the LY-1 is therefore not measured in rounds, but in liters of diesel fuel in its armored tank. As long as it can be refueled, it can continue to engage targets. This entire process, however, is spectacularly inefficient. The very physics of solid-state lasers dictates that for every watt of light projected, 3 to 4 watts are lost as waste heat. A 150 kilowatt beam thus generates a staggering thermal load of at least 450 kilobars that must be managed and dissipated instantly. Failure to do so would cause the laser diodes to overheat and destroy themselves in seconds. Consequently, the thermal management system is arguably the most complex and critical subsystem on the vehicle, occupying a significant portion of its internal volume and weight. It is a 3-circuit liquid cooling system. The primary loop circulates a deionized water glycol mixture through microchannel cold plates mounted directly to the laser diode arrays, absorbing the intense, localized heat at its source. This heated fluid is then pumped to an intermediate thermal storage loop, which contains a large phase change material, PCM, heat exchanger. The PCM, a specialized wax-like substance, absorbs the massive thermal spike from a firing sequence by melting, effectively acting as a thermal battery. This is a crucial engineering solution. It allows the final heat rejection system to be. It draws the stored heat from the now solidifying PCM and dumps it into the atmosphere through a series of large armored radiator banks mounted on the vehicle's chassis, assisted by high-velocity fans. The interplay of these systems reveals the fundamental constraint of all mobile-directed energy weapons: size, weight, power, and cooling. SWaP-C. The 150 kilowatt output of the LY-1 is not a limit imposed by laser physics, but a carefully calculated ceiling dictated by what can be realistically powered and cooled on a road-mobile platform. The operational sequence of the LY-1, from detection to destruction, is a marvel of automation, a process that unfolds at machine speed. The engagement begins not with the laser, but with a suite of integrated sensors designed for short-range air defense, SHORE-AD. The primary detection sensor is a compact X-band active electronically scanned array, AISA, radar, capable of 360-degree surveillance and tracking dozens of targets simultaneously. This is supplemented by passive radio frequency sensors that are constantly listening for the characteristic command and control. T correlates these disparate inputs, discarding false positives and fusing multiple detections of the same object into a single, high-fidelity track file. This process is essential for creating an uncluttered, unambiguous common operational picture for the human operator and the fire control system. In a modern battle space, particularly one saturated with a drone swarm, a human operator simply cannot process the incoming data fast enough to manually track, prioritize, and engage multiple, fast-moving threats. The LY-1 therefore relies on an AI-driven fire control system to manage the engagement. This system employs machine learning algorithms trained on vast datasets of real and simulated threat profiles to perform several critical functions in milliseconds. First, it identifies and classifies the fused sensor tracks, distinguishing a hostile Group 2 UAS from a non-threatening flock of birds. Second, it analyzes the target's flight path, speed. Finally, the AI calculates the optimal engagement solution. This includes selecting the precise aim point on the target, the delicate optical sensor, a control surface, or the explosive payload, and determining the required dwell time, the duration the laser must remain on that spot to achieve the desired effect, thereby conserving energy for the next target in the queue. This software is the true heart of the weapon. While the hardware determines the system's potential lethality, it is the fire control algorithm that dictates its actual battlefield effectiveness. The competition in directed energy is rapidly becoming an algorithm war. Once the AI has locked a target and the human operator gives consent to fire, the system unleashes its energy with a flexibility that no kinetic weapon can match. A high-energy laser, HEL, offers a unique capability for scale. At its full 150 kilobar power, the continuous wave infrared laser beam becomes a tool of thermal destruction. It is, in essence, a blowtorch delivered at the speed of light. The focused energy is dumped onto a small spot on the target surface, and the effects are swift and catastrophic. The beam can melt through an aircraft's aluminum skin in seconds, causing structural failure. It can penetrate the casing of a munition, heating the explosive filler to its detonation point. Or it can simply cook the sensitive microelectronics within the target's guidance system, rendering it inert. The LY-1 does not operate in a vacuum. It is part of a global trend towards operationalizing directed energy. A comparative analysis places its capabilities in stark relief. The United States Army's DEM Shored system, for example, integrates a 50 kilobar laser onto a Stryker armored vehicle. This places it in a lower power class than the LY-1, likely reflecting a different doctrinal role focused on providing direct protection for maneuvering combat brigades, where mobility and a smaller footprint are paramount. The LY-1, with its 150 kilowatts output and larger chassis, appears to be designed for a more stationary role, such as the point defense of critical assets like air bases, command posts, or logistical hubs, where its greater power and range are more valuable than its tactical mobility. Israel's Iron Beam system offers another point of comparison. At a 100 kilobar power class, it is a peer competitor to the Iron Beam is a containerized, semi-mobile system designed to be deeply integrated into Israel's national air defense network, acting as a low-cost adjunct to the Iron Dome's kinetic interceptors. The LY-1, by contrast, is presented as a fully autonomous road-mobile system capable of independent operation or integration into a larger network. Despite its formidable capabilities, however, the LY-1 is beholden to the fundamental and unforgiving physics of atmospheric propagation. The notion of a laser beam traveling unimpeded through the air is a fiction. The atmosphere is an active, often hostile, medium. Water vapor and carbon dioxide molecules absorb photons at specific infrared wavelengths, converting the beam. More significantly, airborne particulates, dust, smoke, fog, rain, and even pollution physically scatter photons out of the beam's path. This effect, known as me-scattering, dramatically reduces the amount of energy that actually reaches the target. Furthermore, the laser's own energy heats the column of air it travels through, creating a pocket of lower density air that acts as a negative lens, causing the beam to spread out and lose focus, a phenomenon known as it is not a rugged piece of equipment that can be maintained with a wrench and a hammer in a forward motor pool. Its high-purity coolants, delicate fiber optics, and sensitive electronics require specialized technicians and a clean, controlled environment for repair. The contrast between its futuristic speed of light engagement and its mundane vulnerabilities can be stark. A multi-million-dollar air defense system capable of incinerating drones in seconds can be rendered completely ineffective by the morning fog rolling in off the coast, or sidelined by a faulty coolant pump that requires a specialist to be flown in from a rear echelon depot. And its most fundamental limitation remains. It is a line-of-sight weapon. It cannot engage a target behind a hill. This introduces a new tactical variable into warfare, the due forecast. Commanders will have to plan operations not just around weather that affects aircraft or ground troops, but around specific atmospheric conditions, humidity, visibility, and turbulence that directly impact the effectiveness of their laser defenses. An adversary could deliberately time a drone swarm attack to coincide with a rain squall or deploy. Looking forward, the LY-1 platform is designed with modernization in mind. Its modular architecture allows for the progressive upgrading of its core components as technology matures. The most obvious pathway is power scaling. The defense industry is already developing 300 kilowatt class laser systems, and integrating such a weapon into the LY-1 chassis is a logical next step. This would, however, necessitate a complete redesign of the power generation and thermal management systems, potentially requiring a larger vehicle or a separate trailer-mounted support module to handle the immense electrical and thermal loads. Beyond raw power, the most significant upgrades will be in software. Improved AI algorithms, trained on ever larger data sets from real-world engagements, will enhance the system's ability to track more complex targets, better discriminate between threats and non-threats, and optimize its energy usage against swarm attacks. Deeper integration into networked battle management systems will allow the LY-1 to engage. The ultimate goal for directed energy is the development of megawatt-class weapons, but these systems, with their colossal power and cooling requirements, will likely be strategic assets confined to fixed sites or large naval vessels for the foreseeable future. The true strategic impact of the LY-1 and its contemporaries is not that they make kinetic interceptors obsolete, but that they fundamentally alter the economic calculus. A defender is forced to use a missile costing hundreds of thousands of dollars to destroy an attacking drone that may have cost only a few thousand. In a war of attrition, an adversary can bankrupt a technologically superior force by launching waves of these low-cost threats. The LY-1 is the direct counter to this strategy. While its initial acquisition cost is substantial, its marginal cost per shot is negligible. Essentially, the cost of the diesel fuel required to generate the electricity. It provides a deep magazine, low-cost defensive layer capable of engaging hundreds of targets at a sustainable cost. This allows commanders to preserve their limited and expensive stocks of advanced kinetic interceptors for high-end threats like stealth aircraft, cruise missiles, and hypersonic weapons. The LY-1 is not a silver bullet, but a game-changing tool. It is a weapon born as much from the minds of accountants and strategists as from physicists and engineers, designed to restore economic equilibrium to the asymmetric battlefields of the 21st century. In the unforgiving calculus of modern warfare, there are no points for second place. Every bolt, every composite panel, every line of code within a weapon system is a testament to a brutal process of trade-offs, where the laws of physics are negotiated against the constraints of budget and the urgent demands of the battlefield. It is a world where innovation is not a matter of elegance, but of survival. Into this arena rolls the LY-1, a machine that is less a truck with a weapon and more a self-contained ecosystem of directed energy. It is the physical manifestation of decades of painstaking, often frustrating progress in solid-state physics, thermal management, and high-speed data processing.